So I'm happy that we can now have this meeting or celebrating your anniversary. So good health and good energy, for your future plan, Dan. Actually, my talk has to do something with the destiny. So with my introduction, do I have time? Actually,
yes. Go ahead.
Okay. Minus 10 minutes.
Yes, please.
I'll be talking about actually most of the speakers was talking about shockwaves. So I want to kind of go in opposite direction. So what happens if shockwave is something that appears in essentially all conservation laws. When you remove viscosity, and it is something which appears and never disappears. So it's totally stable object. So the question, so this is some stable, and there is the theory which proves that it's stable. Essentially, Kevin made a great contribution to this. He will be talk just next to me. So I want to pose the question when it can be unstable. And if it's unstable, what happens? So I will give the example. Okay, so I will start with the Burger's equation, which gives the idea. So you know if that in the Burger's equation, if you remove viscosity, you get initial profile. It becomes and it falls. So it overturns. So you get infinite derivative, and then it becomes a shock wave. And it's a unique solution. So you can make it conditions. You can put conditions that you make it unique. So what I will be considering is really not only when the shock is unstable, but what will happen exactly around that initial moment when it starts. So to understand this, we should understand a little bit some properties of the shock in Burger's equation. So essentially, this is a profile which turns. So it becomes with increasing time, it becomes steeper and steeper. But now, if you renormalize the small piece near the singularity and stretch it in all directions, they converge to a universal curve, which is just this formula without correction. So there is a universality. And this is something easy. In fact, though it was only mentioned in relatively recently, because it's a good example for universality of different types of blow up that we have in PDEs. But you can make a dynamical version of this relation. Essentially, the blow up is something which is contracting to a point. So it's essentially looks like multiplicative process. So we know that multiplicative process we can make convert to summation through taking logarithm. So essentially, this is what's done. You take new time, which is logarithm of all time, new coordinate, which is logarithm of all x. You change a little bit u variable to v, and you get new equation. And it is still translation invariant. And this translation invariant because translation invariant is a new equation corresponds to scaling invariant in Burger's. Now you just take the blow-up solution, substitute, and you get actually the blow-up solution become a traveling wave. So with this mapping, you map the blow-up solution to a traveling wave, and to understand what happens, so we have time, we have blow-up time, let's put it to 0. So we have our new time tau is minus log minus t. So it puts 0 to plus infinity. So you stretch the time so that you arrive to blow up at plus infinity. And the blow up solution become a traveling wave. So this is why, essentially, this is one of the pictures which shows why blow up always happens in the same form, because it in fact asymptotically in the same form, because it has attractor for this rescaled equation. It is globally stable traveling wave. But
Do something analogous
it's well for any scalar conservation law is the same, and there is a good rigorous results that suggest that it's also the same for systems in one dimension. Okay. So what is interesting that you can do this exactly the same after the blow up. So you can make similar transformation, but it will be slightly different because now tau is just will be log t. So you make renormalize everything after, also change x, so just some signs are different. So you have another evolution, but the blow-up time becomes minus infinity. And you also have traveling wave solution, and this traveling wave solution actually it describes self-similar opening of from the singularity to a shock. So it's self-similar, and it corresponds to also to the traveling wave. So now traveling waves, but what is crucial is minus infinity, which means that any finite time, real time, correspond to infinite evolution of our renormalized system, which suggests that our selection principle, which we select, well, you know that weak solutions for Burgers are not unique. So the selection principle actually selects an attractor, because whenever we start, since we have infinite time evolution, we will come out to attractor. So actually the solution which we always observe, which is opening of the shock from singularity, is just directly following attractor for the renormalized system. You can see it directly from the, well, since for Burgers you have everything explicitly, you can see directly from analysis. So this is essentially a moment where we can get in. So we have a traveling wave which is stable, essentially globally stable, and it describes opening of the shock. So what happens if it's unstable? So this doesn't happen for conservation laws, but we will manufacture. I will use this, engineer the system where it happens. So we still will consider conservation law, but we know for we put viscous term, but finally we will remove it. But we will need the flux function. Well, it will not work if it's normal conservation law. So flux function, we will take flux function non-local. So we will take it quadratic, like in Burgers, but with a kernel. And this is exactly the kernel that we will look to. The reason for this kernel is, first of all, the main reason for this kernel is when you make Fourier transform, it just becomes some combination of delta functions. So in Fourier space, the whole of this equation, which is a bit heavy, but it becomes discrete. So when you put in the Fourier space, it becomes discrete, and is discrete on somewhat geometric lattice. So, well, I won't talk too much, but what is important is that instead of, if you do numerical simulation, instead of this equation, which is one dimensional, so it's heavy to simulate, you can simulate strictly equivalent discrete equation. So you can essentially reach viscosity, so like 10 minus 15. So you can really simulate very deeply to the inviscid limit. And another property is that this system is actually quite famous. This is a toy model for three-dimensional turbulence. And there is probably hundreds of papers studying it from perspective of turbulence. Though it's a very hard toy because essentially it's still unknown how to explain turbulence even in this model. So this model, it was, well, very good. It's an infinite dimensional system. Yeah, it is an infinite dimensional system. So essentially, this system has blow up. The blow up is slightly different. So for Burgers, at the blow up time, so at T0, we have x minus 1/3 singularity. And in this system, it is already at the blow up point. It becomes discontinuous. Well, it's similar to the behavior of UX for the Burgers. So it blows up, and we have essentially we have analytically the form how local form of a bifurcation. So the question, what happens next? And what happens next is we can make the whole, we can make the same renormalization of the system going to the log time. It will be still translation varied system, and it gives a traveling wave solution. But this traveling wave is not, well, it's not actually traveling wave. It's a chaotic wave. It's a wave which travels with constant speed, but chaotically. And again, I remind you that any time physical corresponds to infinite time evolution in renormalized time. So as we did for burgers, we have to take a attractor, because any other solution, because since we have the renormalized time that we passed from the blow up to any finite moment is infinitely long in tau. So the only thing we can choose is an attractor. So this means that at any finite time, but attractor in chaotic wave is a probability distribution. So this means that our selection principle does not select a single solution. It selects the probability distribution uniquely at every given time. Just taking the attractor, just directly from the attractor of the renormalized system, because instead of like traveling wave, which you can think about it at fixed point, we have now chaotic evolution. So attractor is a probability measure, and we can see it directly. So this is numerical simulation. So what is here? So tau is our renormalized time. Omega is some special combinations of the it's actually Fourier component calculated at one point and another point, and we take a difference. So this, well, why we choose special representation is related to some Kolmogorov theory. I won't get into it, but what you see is a result of what we do. So we take 100 times random realizations. We put very, very small viscosity, because without viscosity we cannot solve it. And we put very, very small perturbation. So, we see that, and we compute the probability distribution numerically. And we directly see that it behaves as I said, that it's a chaotic traveling wave, but after very small time, it becomes just a propagating probabilistic measure. And we see directly that this is a probabilistic, traveling probabilistic measure. So, essentially, this is summary. I probably rephrase it as a summary. So what this example shows is the following. So unlike in the conservation laws that we're used to, where the flux function is the local function of u, where we always have blow up, and after blow up it uniquely goes to the shock. So if you have a non-local flux function after the blow up, there is unique choice of solution, but in the sense of the probability distributions. So the realization is strongly not unique. You go to, so what you would observe physically is absolutely non-repeatable realizations. But what you uniquely choose is the probability distribution for every realization. And what is interesting, in both cases we have fully deterministic setting. So this is a deterministic equation with inviscid limit, deterministic initial condition, but after blow up in Burgers you continue with a shock with a unique solution. After blow up in this system you continue with a probability measure. So somehow you physically never know where you go, but you have a very well-defined probability the way you go. And this probability appears spontaneously at the singularity. So essentially, this should not be mixed with chaos, because chaos, in a chaos, you have a spontaneous, you have a formation of the probabilistic measure at infinite time. So here it is formed at finite time. So it's immediately. So that's, thank you.
Questions, comments, please.
In experiments, what do you observe?
Oh, in numerical?
Yes.
Well,
physical.
No. Actually, this is a toy model for turbulence. Actually, we now look for systems where you really can see it in the physical reality, but in turbulence itself, there is no still hope to apply it, because you need this finite time singularity, and this is a big open problem for Euler equations. So we don't know even if it exists or not. So we actually try to find some different setting where this can happen. And anyway, what we see is this is a generic phenomenon. So it is a structurally stable phenomenon. So we believe that we will find a good physical system where it will happen. But so far we just have mathematical parts.
So which application you have in mind? You wrote incompressible flow.
Yeah, non-locality comes from incompressible flow. So there are, we need a finite time singularity. And finite time singularity, well, for Euler we don't know. Still there is a good indication that it may happen on the boundary. And so we essentially, what we have to find is where there is a finite time singularity and where the behavior from that singularity is chaotic. So these are two ingredients which together give you the selection principle, the probability measure selected as a solution after that point. So we need finite time blow up and chaotic opening of this blow up point.
So this is related to the Boltzmann?
No. It's fully macroscopic. So you essentially it's probably also on the waves, maybe in waveguide. So you need a finite time blow up, and you need to continue from that blow up. Well, finite time blow up is a typical feature, but the question that after blow up you need chaos. If you put it together, you have this solution. And mathematical examples we have. Now the question of physical examples.
How universal is this probability distribution after blow up?
Well, it does not depend neither on how you perturb, not or how it doesn't. Certainly, you have to put some perturbation that you send to zero, but it does not depend. It's already the inviscid system itself already knows what will be what will be the solution. It does not depend on the way how you regularize, and you have to regularize and send it to zero. Like put viscosity, put some small noise, and send it to zero. But it's fully independent on how you do it. So it is, in that sense, it's universal.
So this happens also with Buckley-Leverett, if you like?
No, because it's local. It should be non-local flux. The flux function should be should depend on the state in the neighborhood. Well, if in some situation you have it, and if it's strong enough to generate chaotic behavior, then it would be the case. Well, but yes, I don't know.